we're finishing up today. So we're going to finish up chapter 13. We'll do some more examples of calculating concentrations, and then we're going to go into working some of the problems at the end of the chapter. These will be recorded as two separate videos, so one will be under the lecture notes, and then the end of chapter problems are in a different location. It's just a different folder so you can navigate to them a little easier. So last thing that we did yesterday is we took this group of problems where we had the same mass of the solute and solvent, and we calculated all these different forms of concentration. So this was the mole fraction. We went back and did one that was percent by mass. We did molality. We did molarity. We're going to continue with that theme, do a couple of different other problems. It's just important that I want you to see as many examples as we can, that you have a handle on how to calculate concentrations and do these types of conversions. So the next example, it says the solution of ammonia is made by dissolving 35 grams of ammonia in 90 grams of water. It says the density of the solution is given. What is the molarity of the solution? All right, so a couple of things. I don't think I didn't put the molar mass in. Let's see. So ammonia, NH3, has a molar mass of 17.03 grams per mole. Usually I try to put that in the problem, grams per mole. Okay. All right. So what we're looking for is molarity. So we want to find capital M moles of ammonia, NH3, over liters of solution. So that's where we need to get to, is finding those two things. Okay, so if we think about the things that we know, first we could calculate the moles. So the moles are equal to the 35 grams of NH3 divided by the molar mass, which is 17.03 grams per mole of ammonia, and we can deduce the number of moles. Grams cancel out, so it's a little bit more than 2. Yeah, we'll just keep an extra digit for try to save to not have rounding errors. Keep an extra digit for your calculations and then save that at the end. All right, the little bit greater challenge is what is the volume of the solution. So if we think about the solution is equal to the solvent plus the solute. So in this case, the mass of each one of those things, we know we've got a certain mass of ammonia, the solute, and a certain mass of water. And those two things to put together, the 35 grams plus the 90 grams is going to equal to 125 grams combined. So that's the mass of the solution. Now we can use the density that's provided. So density equals to mass divided by volume. We know what the mass is, we know what the density is, so we can rearrange that equation and find out what the volume is. So when we rearrange the density equation, it tells me that volume is equal to mass divided by the density. So the mass was 125 grams. The density is 0.898 grams per milliliter. My unit's right, grams per milliliter. So grams would cancel out. Milliliters would go to the top on units. So when I divide that out, I've got the 125, 1.898. So it's 139.1 milliliters. Okay, so calculate the volume. I need it in liters of solution. So to go from milliliters to liters, I move the decimal place to the left 3 times. So it's 0.1391 liters. Moles per liter is what I want. So that's going to allow me to calculate what my concentration is. And I get that this particular solution is 14.8 molar. And actually, since I've only got 2 significant figures in this one, probably need to take that to 15 molar to be more correct. Okay, kind of the trick on this problem that makes it a little bit different is we're giving the mass of these two, solute and solvent, and we have to use that in combination to find the total mass of the solution, then use density to find the volume of the solution. Okay, so it's not anything we haven't seen before. It's just that's the information that's provided.
So everything except for molality, bottom of that fraction is going to be like the solution.
That's correct. Yeah, molality is the only one that's different. So it's kilograms of solvent, not solution. Everything else is solution on the bottom. Whether it's grams of solution, liters of solution, everything but molality is solution. Okay. All right. Here's another example. It says, what is the molality of a solution that is 4 molar in NaOH, and it gives me the density of the solution. So this one we're actually pretty close. We know that there are 4 moles of NaOH per a liter of solution. And what we need to convert that to, so that's our molarity. We need to convert that into molality, which is going to be moles of NaOH per kilogram of the solvent. And it doesn't say that the solvent's water, but it is. So maybe to give you that information, this needs the word aqueous in it. So aqueous means it's a water-based solution. All right, so per kilogram of water. Okay, so this is going to be kind of like the previous problem, except now we're going the opposite direction. So when you've got something like this, you assume you've got 1 liter. Okay, so let's assume that I have 1 liter of the solution. So if it's 1 liter, that's equal to 1,000 milliliters. All right. So if I've got 1,000 milliliters of it, and the density is 1.04 grams per milliliter of the solution, milliliters would cancel out. That means that 1 liter has 1,040 grams of solution as equivalent weight. But what I need is not the weight of the solution. I need the weight of the solvent, which is just the water. Okay, so per that liter, how much of that is the mass of the solution is equal to the mass of the solvent plus the mass of the solute. And this is the one that I'm looking for. So I know the mass of the solution is 1,040 grams. So what I need to do is find out how much solute is in that 1 liter.
Just take the molar mass.
Okay, so that's exactly what we do. If we have 1 liter of it, we know there are 4 moles in that liter. So this is another case. So NaOH weighs, sodium's about 23. Oxygen is 16. Oxygen is 16. And hydrogen is 1. So it weighs right at 40 grams per mole. Okay, so that's its molar mass. So if that's the grams per mole times 4 moles of it, that means that there are 160 grams of sodium hydroxide in that liter of solution. So mass of the solvent plus the mass of the solute, there's 160 grams of the solute in there. So now if I subtract over the mass of the solvent, is going to be the 1040 minus the 160, so 880 grams of water. And I need it to be in kilograms, so I'm going to move the decimal place to the left 3 times. 0.880 kilograms. So now going back into plugging into the problem, the molality is the 4 moles of the solute divided by the mass of the solvent, which is 0.80 kilograms. And we only have 2 significant figures, so we need to take to this one to 2, 4.5 more. And the rule that, just to see if you're doing the calculations right, is that if the density is greater than 1, typically the molal is going to go up. If the density is less than 1, the molality is going to be less than the molarity. Okay? And if they're equal to each other, it depends on concentration. If their density is equal to 1, they'll be pretty close, but it depends on, is it a high concentration solution or a low concentration solution. If it's less than like a 10th molal, molarity and molality may be very close to one another. But when you get something that's got 4 moles in a liter, that's more than 10% of the mass. It's a lot of it. So you have to take that into account. Right?
Okay, I have a question, not exactly on the problem. On the chest, like for those down there, is the question going to say, like, what is the parts per million by mass of? Is that how it's going to be set up? It'll say, whenever we say a part per million, part per billion, those are always by mass. And what is the parts by volume?
The part per volume, so these are percents by mass, these are parts by volume. So the same way that you can have a percent volume, it's a part per 100. So if we say a percent volume. So it'd be milliliters of solute divided by milliliters of solution. Okay, and we'll work some examples of all of those at the end of the chapter. Okay, so coming forward. Okay, one more. So got a solution that's prepared by taking a certain mass of a solute, sodium iodide. At this time I did put down the molar mass. I put it in a certain mass of water, and I want to know the mole fraction if the final volume of the solution is 517 milliliters. So those are the things that I need to know in the system. So the mole fraction of the solute, so that's the sodium iodide, is the solute, is equal to the moles of sodium iodide divided by the moles total. And just remember the range of numbers it can be anywhere from 0, no moles of it, to, if it was all of it, 1. So if you ever get a number greater than 1, something's wrong with your calculation. Right? So we simply need to calculate the moles of each one of those things and plug in to our numbers. So let's calculate the moles of each. So start with the sodium iodide. I've got 76.3 grams of sodium iodide. And it's a pretty heavy compound because of the mass of the iodide that's so high. It weighs 149 grams per mole. So that's a little bit less than a half, pretty close to half a mole. a little bit more. So we've got 0.09 or 0.509 moles of the solute. So now we do a similar thing for the water. There's 554 grams of the solvent in water. Water weighs 18.02 grams per mole. Grams would cancel out, same as they did above. So 545, 18.02. And we've got 30.244 moles of water. We'll round at the end. So now plug into my equation. The moles of the solute on top. On bottom, I put the moles of the solute plus the moles of the solvent. Let's see, I've got 3 significant figures and everything. So I need to take that to 0.0166. 3 decimal places. Or 3 significant figures. 4 decimal places. 3 significant figures. If I ask what was the percentage mole fraction, I just take that and multiply it by 100. And it'd be 1.66% of that solute. Okay. All right. So here's you one. So you've got a solution that's got an initial concentration in molarity, and I want to know what is the molality if I give you the density. And molarity, just to remind you, is moles per liter of solution. Molality is moles per kilogram of solvent. Okay? Work that out. 3 more answers. Last one. Okay. All in. So most of you went with choice B. 2 of you chose choice C, but I don't know what the answer is, so I've got to work it out. All right. So start with writing the form of the concentration that you know. So there was 0.387 moles of HCl per liter of solution. Okay, so we need to convert that from liters of solution to kilograms of solvent on the bottom. So the moles of HCl on the top part of it are where we need to be. So we're set there. We just have to work on the bottom half of it. So it tells me the density of the solution is 1.23 grams of solution per milliliter. And then I've got a milliliters to liters mismatch, so I need to get those in a common unit. So if I look at where I'm at now, my liters of solution and liters cancel out. My milliliters and milliliters cancel out. I've got grams of solution. So that's close to where I want to be, but I need to be at kilograms of solvent. So the thing I need to know is how much of that solution is actually solvent in the system. Okay, so if I know what the solid is, we can go back to what we did in the previous problem. The mass of the solvent is going to be the mass of the solution less the mass of the solute. Okay, so we know the mass of the solution is, if we assume that it's a liter of it, we multiply that out, that's 1,230 grams. Now, how much of that is the solute? Well, we know the number of moles, so if there's this many moles per 1 liter, and we know the molar mass, that means that there's 14.1 grams of HCl. So what I did was just take the mass of the HCl is equal to the moles of the HCl, which is the point, whatever the concentration is, times the molar mass, which was the 35.46. Now let's subtract those out. It tells me that there are 1,216 grams of the solvent there. And I'm not sure what the solvent is. I assume it's aqueous, but it doesn't. Yeah, it does. It tells me it's water. So aqueous, it's water in our system. So if I convert that from grams to kilograms, it's going to be 1.216 kilograms of water as the solvent in the system. Okay, so now I can just take the problem and do the conversion in that way. Per this 100 or 1.23 grams of solution, right, there are 1.3 6 kilograms of water. And this is times 10 to the third to get those to multiply out. Or you just could have took this number of moles and divided it by this number, but I'm just letting those two things cancel out. And number I get is choice B. Okay. And let's see. Was that our most predominant answer? We get there. There it is. Yeah, choice B. So most of you are on track. If you didn't correct for the solvent out of the system, I think you come up with choice C, which is the other component in it. So if you didn't correct for the solvent. Okay. Pieces to a puzzle.
I have a question.
Yes.
How did you get the 14.1 again? Took the molar mass of HCl and...
Yeah. So we assume we had 1 liter of it. So I simply took the number of moles that we had. So it was this number of moles per liter and multiplied it by the molar mass, the 13. So I put that times each other. Okay. And that's where the 14.1 came from. That's the mass of the HCl. Okay. And again, the thing I'll tell you, my advice is practice makes perfect. The more exposure or experience you have to these types of problems, the more comfortable you'll feel with doing these types of conversions. Okay, switching over to a different topic to finish the chapter up, and that topic is colligative properties. And colligative properties are properties that depend only on the number of solute particles and not what the solute particles are. So when we think about the changes that are made by the introduction of a property, we're looking at changes that only depend on the concentration of the solution and not really what the solution is made out of, which is kind of weird, but that's the way chemistry has this odd behavior. Sometimes it's not what we expect. So the differences that we observed in the property of the solution related to the pure solvent in the system is due to the differences in the attractive forces we have. And what happens is when we put a solute particle in solution, it occupies some of the sites where the solvent would normally be in position, and it takes place in that and alters both the boiling point and the freezing point. Those are the two main ways that we see those things. When we look at the boiling point, the way that we measure a boiling point is by looking at a vapor pressure, and as that vapor pressure is atmospheric pressure, that's where we see the biggest change. That's defined as the boiling point. So what happens, the vapor pressure of a solvent itself compared to that of a solution, that when the equilibrium establishes for the pure solvent, it's different than what happens when you have a solution. Because when a solution occurs, some of the solute particles get into the surface and they block some of the solvent from going down the solution. Therefore, not as much can be volatile as volatile, so the rate of vaporization is reduced by the presence of the solute. If we look at how much is it reduced, well, it depends on how much of the solute molecules are present, and if we start to get a larger and larger percentage of the solute particles on the surface, we get a lower and lower vapor pressure compared to the pure solvent. So what we always see is there's a reduction in the vapor pressure as the equilibria is reestablished and a solute has dissolved. One way that we can demonstrate this behavior is with a topic called thirsty solutions. So a concentrated solution will draw a solvent molecules towards it, and it will tend to dilute a more concentrated solution. We talked about this at the start of the chapter with the salt water and what happens in your intestines. Okay, it's pretty easy to actually demonstrate, by taking and putting these two things next to each other and putting it into, if you want to do it at your home, so next time you go home to grandma's and she's got the clear cake display thing. So you take that bell jar and you put a cup of two coffee cups, and you put a bunch of salt in one and dissolve some water in it. And then you put just pure water on the other side, and you put the cake cover on it. Let it sit there overnight. They'll start off at the same level, but what happened, the one with the salt in it wants to be diluted down. It's thirsty. So it will actually take the water molecules that are in the vapor phase, and as these vaporize and they fill the container, some of them now get reincorporated in this one because that solution wants to be at the same concentration as this one, even though they're not connected physically, they're connected through the vapor phase. So if you let it sit there overnight and come back, what you'll see is that one cup is greatly diminished, the other cup increases by the amount the other one went down. What we call a thirsty solution. So we can see these colligative properties occur in very simple demonstrations and show that they work. Now, the quantitative way that we account for this is something called Verlox Law, and I'm describing it first for non-volatile solutes. So this wording wasn't here, so I added that to my notes. So if you have notes printed out, you may write that. So this is taking a volatile solvent and adding a non-volatile solute to it. We'll talk about if it's a volatile solute in a couple of slides. So what happens to the vapor pressure is that the vapor pressure of the solution that contains this volatile solvent is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So we know the normal vapor pressure of the pure solvent. We simply need to calculate what the mole fraction is. This was the Chi's that we did on the previous slides, talking about those. And we know a mole fraction is always less than 1. The 1's as big as it can possibly be. If it's the pure solvent, Chi is 1. So the vapor pressure of the solvent is just equal to that of the pure solvent. So what we see is a reduction in the vapor pressure. So it's always going to be less than that of the pure solvent whenever I have a solution of a solvent, I have a substance dissolved. So it's a vapor pressure reduction. The fact that we have this solution causes the vapor pressure to go down compared to that of the pure solvent, and it's always going in that direction. How much it goes down is proportional to the amount of the solvent that's present in the solution. So it goes back to this mole fraction. The larger this mole fraction is, the larger the solvent, means the larger the vapor pressure is going to be for the particular system that you're studying. So we can look at this as being the difference in the vapor pressure of the pure solvent less the vapor pressure of the solution in the system, and the difference in the vapor pressure is simply the difference in the vapor pressure of the pure solvent less of the solution, which we said the difference is the Chi, the vapor pressure now of the solute, not the solvent, times the vapor pressure of the pure solvent. So this is equal to the amount of the lowering that occurs. How much does the vapor pressure go down? Well, how much of the solute's there is what it comes down to. Is it a small amount of mole fraction or is it a large amount of mole fraction? So where does this have any practical application? We see this type of application in a number of different things. One of the common ways that we see this change in vapor pressure occur is we look at do we want something to be volatile or do we not want it to be volatile? So if we want to stabilize something that is that's a highly volatile substance, we can put something in it to lower its effective vapor pressure. Right? So if you don't want your paint to evaporate as quickly, if it's a hot day, there's things that painters can put something in. So if it's real hot and you spray paint or lay down paint before you have the chance to either brush it or smooth it out, it start drying. So they can put things in the paint to make it slow down its drying process, so it won't go to the vapor phase so quickly. That way it gives you time to work the paint in. Those are the chemistry of it, they don't understand necessarily at the paint store, but they know, put a packet of this in your gallon of paint, it will slow down the vaporization process. So there's practical aspects of this that we use all the time. All right. Now, if both substances are volatile, it's a little bit more complicated. When both the solvent and the solute can evaporate, both species are going to be found in the vapor pressure. And the total vapor pressure is the sum of the vapor pressure of each one of those components, so the vapor pressure from the solute plus the solvent. So for an ideal solution, what we would just simply do is add together the vapor pressure for each component, and that equals the total vapor pressure, much like we talked about with the ideal gas law and ideal gases and solutions. We can express that in terms of the mole fractions. So the vapor pressure of the solute is equal to the mole fraction of the solute times the vapor pressure of the pure solute. The the vapor pressure of the solvent is the mole fraction for the solvent times the vapor pressure of the pure solvent. Our problem is not everything works in this ideal world. Same way that we looked at gases back in chapter 4, because of the types of intermolecular forces that occur. When you make solutions, we have these solute-solvent interactions that we've talked about in the previous chapter, as well as some in this chapter, and we have to break those bonds to make this new solution. We have to break the solute-solute interactions and the solvent-solvent interactions. We got to make a hole to put these new compounds in. If the sum of the bonds broken versus the bonds formed was the same to what the original solvent was, it would follow an ideal, and those things would be completely additive. What we'd effectively be doing is diluting the solvent down. If the interactions are stronger or weaker than what we initially had from the solvent-solvent or the solute-solute, the solution is non-ideal and things don't add together quite in a one-to-one combination. Okay, so whenever the solvent-solute interactions are stronger than the solute-solute plus the solvent-solvent, so this is going to be something that's going to have very strong intermolecular forces between the compounds. Okay, what happens is the total vapor pressure is going to be larger or going to be less than that than we predict by Verlox Law. What's happening, instead of going into the gas phase, the things are sticking together too much, or more than we would predict. So it causes the vapor pressure of the solute and the solvent to be lower than ideal. Now the opposite is also true. If the interactions are weaker than the solute-solute or the solvent-solvent, now the vapor pressure is higher than we predict by just simply adding the individual vapor pressures together. So this graph kind of demonstrates that process occurring. On the left-hand side is an ideal solution. So what you have is the mole fraction for the different components and the vapor pressure plotted on this side. So if we look at on the substance A, so the mole fraction for A, looking at my curve, is shown with the red line. So when its mole fraction at 1, it's pure solvent A. And the total vapor pressure equals its vapor pressure. So whenever the partial or the mole fraction for A goes to 0, that means we're pure component B and the vapor pressure is this pressure. For any point for an ideal system, if we went to, let's say, 0.4, the vapor pressure would be additive of what it is from component A plus what it is from component B, and those two things add together would give you the vapor pressure of the system. Okay, but if it's non-ideal, so what happens when you have strong solute-solvent interactions? It causes the sagging of the total vapor pressure curve. Now the things are sticking together too much. So it's a little bit lower than we predict it to be ideally. The ideally would be the dashed line, but it's lower than we expect it to see. And when we have the weak interactions between the two, now it's the opposite.
My apologies. I couldn't hear what you said.
I'm glad. I don't know how to turn that off. I'll figure that one out. Okay, so whenever you have weaker interactions, now the deviation's to the positive side. It's higher than what we expect for the ideal mixing in the two. So that's a condition where the vapor pressure is higher than we expect. So if we interact something like the solvents hexane, which is a very nonpolar solvent, and we dissolve it with a little bit of a little bit polar compound, so something like isopropyl alcohol. So isopropanol. So isopropanol, so hexane is C6H14. So carbon, 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 need one more, 6. And then it's got all these hydrogens around it. So the only types of forces it has is dispersion forces or London forces. So it's only carbon-carbon and carbon-hydrogen bonds. Versus isopropyl alcohol. Isopropyl alcohol is somewhat similar. It's 3 carbons, and it's got hydrogens around it. The difference is it's got this polar OH group on it. Now the bulk of the molecule is still nonpolar. So the two things will mix up to about 20%, but it still has this little bit of polar functionality to it. So this would be two things that have weak interactions between the two. So this would be an example of something that has a positive influence on the vapor pressure curve versus something that is a weaker. All right, so here's a question I want you to think about in terms of the interaction. So this is a group question that I'm asking you. So talk to each other. So I've got to consider two solutions. One solution has 10 grams of glucose, which is a sugar. It's C6H12O6. Put it in 1 liter of water. The other solution has 10 grams of sucrose, which is what we call a disaccharide sugar. It's got 2 sugars put together, so it's a little bit bigger. It's C12H22O11, also in a liter of water. So both are non-volatiles, okay? Which of the following statements is true? So y'all can ask each other, figure it out.
Has to do with whichever one's very small.
And put a little pressure on you.
I guess it'll be the. But I thought that had to do with it's either going to be A or B.
Right. 50 seconds.
Half an hour. That makes sense.
Okay, now remember what I told you with colligative properties. Think about what the definition of colligative properties was. That's the key to answering the question.
Oh, okay. Yeah, colligative property not based, or it's not based on what it is, just they both have the same, so they should have the same thing. Should be.
Okay. Everybody's voted. Survey says it's not going to tell us. Okay. I don't know why it appears and then disappears. All right, so most of you went with choice C. And choice C says that both solutions have the same vapor pressure. Right, and your rationale for that was that, I heard somebody say it, that it depends on the amount. Right? But are the amount of the particles of each one of these substances the same? Does it have the same number of moles? Why not? Shaking your head.
Because
One's a lot heavier than the other one by molar mass. So the one that has the most particles in solution is the one with the lowest mass. Okay, it's going to be the one that is going to have the lowest vapor pressure. So the one that's going to be the highest vapor pressure is going to be the one with the fewest number of particles. So the sucrose has more particles, or has fewer particles because it has the higher molar mass, therefore its vapor pressure is going to be higher. The one that's got more things in solution. So if you want to think about visually what that's saying, the one that weighs twice as much, there's 10 grams of it, so it's got the water in here. So you've got the water molecules on the surface. The one that weighs twice as much doesn't have as many particles compared to the one that weighs half as much. So you have twice the number of particles on the surface. This one has a lower vapor pressure. This one has fewer particles on the surface. It has the higher vapor pressure associated with it. Okay. So molar mass does play a role. You're on the right track with your approach to it, but it doesn't matter on the mass. It's the number of particles. Not mass. Okay? So the lighter something is, the more particles it has, the more it influences. And the heavier something is, the fewer particles it has. Okay? The fewer the particles, the higher the vapor pressure. Yep. So that's what's happening because the sucrose, it has the larger molar mass. There's fewer particles, so it has the highest vapor pressure. That's really a critical thinking problem. Very likely to see a problem like that on the exam versus the final exam as well. Right, so you got to put pieces of the puzzle together. Okay, there's a couple of other ways that we monitor these colligative properties, and we actually apply those. We're kind of at the time of year where we use these more frequently. We relate colligative properties to a change in vapor pressure. So vapor pressure lowering occurs at all temperatures, and the way that we can most commonly see this is the vapor pressure at which a solvent boils. That's the boiling point. We did an example of that in lab last week. We also see this change in temperature at the freezing point. So what happens is that the freezing point gets smaller. The boiling point is going to go up. The freezing point is going to go down. So we call these the freezing point depression and the boiling point elevation that occur when we add a solute in the system. So if we look at a comparison line between something like water, so that's the blue line that we have, that's the pure solvent that we have in the system. And if we add something to that, like antifreeze that we add, antifreeze is ethylene glycol, which is a non-volatile compound. It causes both the freezing point to decrease, go to the left, and it causes the boiling point to increase to go to the right. Well, why is that important for us now? Because we don't want the water in our car to freeze when temperature is below 32 degrees outside. All right, so the way that we correct that is typically, depending on your car, you mix your antifreeze to water about a 1-to-1 ratio, depending on what the mixture is, and it causes this depression to be further and further over. The important thing is that it's low enough to be less than what the temperature is outside. So what does it hurt if your motor freezes? Well, because the aqueous solutions expand. When they expand out, they'll take the components of your motor and they'll actually put enough energy on it that it'll blow your block out. So older cast iron blocks have something called freeze plugs in them. They are basically something just pressed in, and the idea is that those freeze plugs would be pushed out when it gets cold. But when your motor starts up again, now your antifreeze or your radiator fluid is just going to run out on the ground because that plug's been pushed out. It protects your motor from freezing and busting. Now, the liquid up inside of the heads where there's no, this portion of the motor, where there's no freeze plugs, frequently you're going to get a cracked head. All right, so you can maybe save the block of the motor, but best thing you can do is just make sure your car's got antifreeze in it. If you're not leaking antifreeze or leaking radiator fluid, rarely do you ever need to change that. It's just something before winter gets there every year, you need to check. Otherwise, you can replace a motor, and that can really get expensive. So how much does this occur, this change that occurs? The difference that we have in the freezing point, we call the delta T sub F, is equal to the molality of the solute, right, times a K sub F. And the K sub F is called the freezing point depression constant. So the value of K sub F depends on what the solvent is. So is it water versus methanol versus something else? And the units of K sub F are degrees Celsius per mol. So this is where the colligative properties come into play down on the bottom. It doesn't matter what the solute particle is I'm putting in the solution, but simply what is their mol. Okay, how much of it's in there? How many moles of particles per kilogram of the solvent? So once I determine the mol, I can multiply it by the K sub F, and I can calculate the change in the freezing point. And remember, it's always going to be a depression. It's getting smaller. So it's going to get the freezing point with the solutes always going to be going in the negative direction. So this table is a table, you may need to refer to this for some of your mastering chemistry problems. It lists some common solvents that we use. It gives us their normal freezing points, and it gives the K sub F values as well as normal boiling points and K sub Bs. K sub Bs are for boiling points. We'll introduce that in our slide or so. And you can see that some of these things have a very significant impact. Some have a lower impact. Now, the most common thing that we use is ethylene glycol that we use for antifreeze. It's not on here because it's not the solvent, it's the particle that's in solution. So we think about if we use water antifreeze mixtures or water ethylene glycol, it's a property of the water, not of the ethylene glycol. Only thing that matters is how much of that ethylene glycol is in there. Now, why do we choose to use ethylene glycol over table salt? And the reason is table salt inside of salt makes salt water. If you know anything about salt water and putting metal in salt water, it's highly corrosive. So it would rust the inside of your block out very, very quickly. Ethylene glycol is used because it is a corrosion inhibitor. Okay, it will keep your inside of your motor from rusting out. But depending on what your solvent is, we can use this to do calculations to find out what the change will be. Now, we look at these changes in a couple of different ways. Sometimes we just want to know what the new freezing point is going to be. Sometimes we can use this in the lab to determine some other properties, something like molar mass. And this is an example of that. We're going to do an experiment very much like this on our next lab that we do next week. We're going to be given an unknown substance. We're going to compare the freezing point of the solvent. Then we're going to put that unknown substance in there. And then from that, we're going to determine the molar mass of that substance by finding out what the freezing point is again. So in this example, lauryl alcohol, it's a component of coconut oil. It's commonly used to make detergents. A solution that has 5 grams of lauryl alcohol and 0.1 kilograms of benzene freezes at 4.1 degrees. I want to know what is the molar mass of lauryl alcohol. And the information that's given is the K sub F from benzene. This just came off that table we looked at. It's 5.12. And the temperature or the freezing point of pure benzene is 5.5. And I've got some equations down here at the bottom that are the things that we're going to use through our calculations. All right, so let's get these things out of the way. Okay, so if I look at the change in temperature, is equal to the mol times the K sub F. So if I want to solve for the molar mass, I need to know something about the number of moles that are going to be in the solution. So the thing I want to solve for is the mole. So if I rearrange that, that says that the mole is equal to the change in the freezing point divided by the K sub F. Well, the change in the freezing point is just going to be going to take the numbers that we had. So it would be the temperature final less temperature initial. All right. So if we think about change in freezing point, it's going to be negative. So the initial minus the final. So that's K sub F. It's the wrong one. Wrong value. So the temperature of the solution freezes at 4.1. The temperature of the pure solvent benzene freezes at 5.5, and that's degrees Celsius. And then divided by the K sub F. So K sub F is 5.12 degrees Celsius per mole. Degrees Celsius are going to cancel out. The mole are going to go to the top. So I just subtract and divide. And I do have those in the wrong order because that has to be you can't have a negative concentration. And I get the molality as 0.273 mole. All right, so switch the orders. Put the pure solvent first. So this would be the temperature of the freezing point of the solvent less the temperature freezing point of the solution. It's the order they need to go in. So now I know the mole in this. All right, so could I, if I think about what is mole is the moles of the solute. In this case, it's fluoroalcohol per kilograms of the solvent. Okay, so I know what the things that I know. I know what the mole is. I just found that. I know how much of the solvent's there. So that was given in the problem. So I know this. I can use this to find out the number of moles that are there. So if I rearrange that equation, the moles of the solute, which is fluoroalcohol, equals the mole times the kilograms of solvent. Just cross multiply. Okay, so the mole is 0.273. So that's moles of solute per kilogram of the solvent times it's 0.1 kilograms of solvent. So kilograms would cancel out. So that tells me the moles, number of moles, is 0.273 moles of solute. So if I want to know molar mass, what are the two things I need to know? What are the units of molar mass? Grams per mole. So it's the grams of the substance divided by the number of moles. So the number of grams was 5 grams divided by the moles, which we found was 0.0273 moles. And I get it's 182.8, round it to 183 grams per mole. That's the molar mass of that compound. So we'll do a very similar thing to this next week in lab. We'll take and measure the freezing point of a pure solvent by itself. we'll take and put a certain mass, measured mass of an unknown compound in, and we're going to know how much of the solvent we have, so we're going to know the mass of the solvent, and then we want to find out what is the freezing point of the solution, take the difference of the two. We can solve for what is the mol, and then knowing how the mass of the compound, we can solve the molar mass of that particular compound. And the neat thing about this, now we have some very expensive devices, so we have something called a mass spectrometer that can measure the molar mass of compounds, and it does that by taking the compound, knocking an electron off of it. In the gas phase, it takes that ion that's created and it manipulates it through a series of electric and magnetic fields, and it determines the molar mass to a couple of decimal places. That instrument costs $150,000. Okay, so this you can do with a thermometer. And you need $10 worth of beakers and some solvent. So sometimes you don't have the $150,000 piece of equipment. We have to do something in a simpler way. And it depends on the accuracy that you need. If I have, and we have these types of problems all the time. One of the things that our department is responsible for in terms of chemistry is everybody else's messes. So when waste disposal happens, we're responsible, since we dispose of chemical waste that we acquire through the course of the semester. The university also gives us everybody else's waste. And sometimes it's things like what the janitor's closet. Sometimes it's 55-gallon drums of something that's been sitting out at maintenance for so long, labels are all falling off of it. So they say, well, you need to dispose of this. First thing we have to answer is, what is this? So we have to do some simple tests to try to figure out what's the density of it. And then we can do a simple test to try to figure out, what's it miscible with? We try to get some idea of what is this compound. Doing a simple test to get an estimate of its molar mass tells us a lot. For us to do that estimate and determine, so we had a few drums that were labeled as pesticides and herbicides that were behind the maintenance building that's over, like you're going towards biology, where they keep the lawnmowers and stuff. They were back behind it, and they weren't what they were labeled. We were quite certain of it, but what was in them was a mystery. Then the drums had been there 40 years, and we had to get those tested by an EPA lab. It cost about $5,000 to get those tested, okay, because it looked like they were pretty much water that was in there. But before the company would dispose of it, we had to verify what was in there. It was water. So it was runoff coming in the building. But we had to pay for the testing by a certified lab to get that done, if we knew the identity of it. So if you ever go into employment somewhere, and it doesn't matter if it's waste that comes from a janitor's closet or motor oil, put it in something for later, because it takes knowing the identity of it, cuts the cost of disposing of that material easily in half. All right. We have a similar type of deviation that occurs with a boiling point. So boiling points can go up. We call it the boiling point elevation. So the boiling point of a solution is higher than that of the solvent itself if it's a non-volatile solute. The formula that we use says the difference in the boiling point is equal to the molality times, this time it's the K sub B. And the K sub B is the boiling point elevation constant. And again, it depends on what the solvent is, not the particle. Only thing that matters are what are the molality of the particles in that solution. And similar to K sub F, it has units of degrees Celsius per a mol in a system. Okay, so work on this one together, or do it individually. So I want you to calculate the freezing point of a solution that has a certain mass of methyl salicylate in it, and I give you its molar mass, dissolved in 800 grams of benzene. And I give you its molar mass if you need it, and I give you the freezing point constant for benzene, and the freezing point of pure benzene is 5.5, as it was in the previous problem. So basically, I want you to apply the change in freezing point to tell me what the new freezing point is. Okay, talk about it. Do it on your own. You got a couple minutes to work on it. So I tell you how much solute's there. Tell you how much solvent's there. You should be able to work out that change in T sub F down at the bottom. I don't care if y'all huddle up to work these. But you need to be able to crank through it.
Okay, so we're still Delta sheet. Okay, so
What now? Oh. Something needed, huh? Alright. Let's throw a little pressure to it. 90 seconds.
But I don't know. Basically changing temperature,
Yeah.
freezing.
Right. If you're going to have to take a guess, can you eliminate an answer? Is there one answer that can't be? Okay. Well, think about that.
How'd you set it up?
I figured out what this is. But I thought you said Delta T was solved line. Solvent minus solution working. That make it 3. Well, then you have a solvent minus solution.
So you know initially it's 5. It's going to be going, it's depression. It's 5.5. It's going to be going down.
I think it's C. Because the whole solution is 2.09, so you'll have to 5.
Okay, 10 seconds. Put an answer in.
See, this is the right answer for the solution.
Okay, so most of you went with C. Not sure if C's right or not, so I'm going to work it with you. So the first thing we need to do is find out what is the molal. So the molal is equal to the 40 grams of the solute. It has a molar mass of 122.12 grams per mole. So that's going to give us 2 moles of the solute. Right. So now I'm going to need to take that and divide it by the mass of the solvent in kilograms. There's 800 grams, which is 0.8 kilograms. $42.8 divided and I get the molality is 0.409, significant for molal. So now I can calculate the delta T, change in freezing point. It's the molality times the freezing point depression constant, K sub F, 5.10 degrees Celsius per molal. That cancels out. 5.1 tells me that the change in freezing point is 2.09 degrees Celsius. So if the freezing point originally was 5.5 and it went down 2.09, what's going to be left is 2.991 degrees Celsius. So like none of those. Okay. Everybody got a math error?
It's the very last. 5 minus.
Oh, I subtracted it, yeah, from 5, not 5.5. Whoopsie. 3.41. And choice C was y'all's most abundant choice. Yes. Because that's the, on all these problems that we're doing, you got to know that before you do anything with it. That's correct. Yep. So, I mean, we know this one, right? So to calculate the change in freezing point, we've got to know what this is. Well, to answer that, I've got to know these two things. I know one of them. I've got to find the other.
So molal is solution. What is this?
Okay, so it's moles, molal is equal to the moles of solute divided by the kilograms of the solvent. Draw a box from that. That's what molal is.
Is that on our sheet?
It is on your equation sheet. Equation sheet's already posted.
Yeah.
I encourage you to print that out and use that working matrix problem. Use it to review your old exam questions. That way you know where to go to on the sheet. Okay. All right, so just a few more slides on these. Talk about Van Hoff factor a second. So Van Hoff factor is a way that we describe if you have a ionic compound that dissolves in the solution. And when those ionic compounds, tongue twisted, when the ionic compounds dissolve in solution, you get multiple particles depending on what the formula unit is. So if it's a 1-to-1 ionic compound, it dissolves into two different particles, a cation and cation and an anion, like sodium chloride. However, some things have different combinations depending on what the charge in the cation and the anion are. So the way that we correct that is what's called the Van Hoff factor, and I is the term that we use to describe that. It's simply the ratio of the number of moles of solute particles per a formula unit dissolved. And typically what happens is the Van Hoff factor is a little bit, in reality, is a little bit less than what we would say it should be theoretically. So frequently what we have to do is do experiments to verify the delta T is really as small as we expect it would. I'll use the example, if you took aluminum nitrate, if you took this and dissolve it in solution, make it aqueous, it dissociates to form the aluminum cation and 3 nitrate anions in solution. So both of these become aqueous in solution. So as one formula unit dissolves, what it ends up in is 4 particles. So what that would mean is that the Van Hoff factor would theoretically be 4. Now, the problem is that it doesn't quite work like that. It actually gets pretty close for some things, but as you get to larger and larger salts, it's a little bit smaller than expected. So the table that's on the right shows what the expected value is versus what we actually measure it to be. So if it's a molecular compound, a non-electrolyte, I simply 1, and it's just the equation that we used before. Something like sodium chloride, that dissociates into 2 particles. We expect it to be 2. It's pretty close to 2. But if you use something that's got higher electrostatic interactions, so like the magnesium 2 plus, the sulfate 2 minus, we expect it to be 2. It's quite a bit lower. It's 1.3. Right? If you look at something like magnesium chloride, so now it's a 1 minus and 2 plus charge interactions electrostatically. We expect it to be 3. It's actually a lot closer. So where it becomes the biggest deviations is when you have the biggest electrostatic interaction between the 2 things. So the higher the charge on both cation and anion. If we look at something like, now put the double charge on the sulfate ion, potassium's a +1, we expect 3, it's 2.6, so those 2 are fairly close to one another. Something like the ferric chloride, we expect it to be 4, much like the one that we did with the aluminum nitrate on the previous page. It's 3.4. So what the reality of this is we have to use the measured term. So where these come into play in our freezing point depressions is that for an ionic compound, the change in freezing point is equal to the molality times the Van Hoff factor times the freezing point depression or elevation if it's boiling point. So we just simply multiply it by whatever this term I is, this factor that shouldn't exist. So if it's an ionic compound, I have to give you the I. Either that or I have to tell you to use the theoretical value, the expected value. Okay?
Okay, so that measured value, what is that representing?
So that's representing going in the lab and dissolving a certain amount of that substance in the lab, knowing the molality of those compounds, measuring the delta F, and determining the experimental value of I.
It's saying particles, so like NaCl would be 2 expected particles.
Okay, so the I, going back to it represents the total number of particles that are produced per formula unit. So if we look at example, sodium chloride would dissociate into the sodium cation and the chlorine anion. There's 2 particles, I expect it to be 2. Magnesium sulfate would dissociate in the magnesium 2 plus.
Yeah. My question is, how do you have half of a particle?
Well, it's not that there's half of a particle there, it's that the influence of it is 1/2. So what happens is these ions are attracted to each other by electrostatic interaction. And the more they stick together, the more effectively they become one particle instead of separate particles. So when you have something that has a much stronger interaction, so something like the magnesium sulfate, so it causes a deviation. So that has a very, very strong attraction because of the 2 plus 2 minus charge. It doesn't act like it's 2 particles. It only acts like it's 1 1/3 particle. So that's what's causing the deviation. Okay. So where I may ask you a question is which one would cause the largest deviation? So I want you to understand this table in terms of how is the difference in the electrostatic interaction changing to cause the biggest difference or the smallest difference between the expected versus the experimental Van Hoff factor. So make sure that you take a glance at that table when you study your notes. If you'll look at the old exams, you'll see a couple questions like that. Okay? Just want you to understand where those are coming from. Okay, so here's the last clicker in the notes. We still got 30 minutes left.
No, I got some practice.
Your coach is killing you.
I know.
Yeah. You're rolling the class to 120. Okay. All right, so what's the ideal Van Hoff factor for magnesium nitrate? Two more. All right. So most of you went with choice B. A couple with the other ones. Let's just think about that particular compound. So magnesium nitrate, when it dissociates, or nitrite, NO2, when it dissociates, it produces the magnesium 2 plus and 2 of the nitrite, 2 minuses. 1 particle, 2 particles, I equals 3. So I expect it to be 3 with this. Okay. So as long as you understand how ionic compounds dissociate, that always tells you you're theoretical. You just add together the total number of cations and total number of anion particles, and we get our solution. All right, another way that we see the effects of colligative properties in the real world is an example of an osmotic solution and osmotic pressure. So something that we say that is isoosmotic, it has the same pressure of the solution inside and outside of the cell. So that means that water doesn't flow in or out through the cell because of pressure. So something that's isoosmotic is our normal cell shape that we have. So what happens if somebody becomes very dehydrated? So they go to hyperosmotic. So your red blood cells that normally kind of look like a Cheerio on one side, right? So they have a normal shape to them, a normal volume of blood. As you become severely dehydrated, your red blood cells shrivel up. They don't function like they should. And the opposite can become true. So if you become hypoosmotic, so your blood cells get so swollen, and as they get higher and higher concentrations of water in there, it dilutes down the contents so they don't function the same way they should function. Right? So they don't have the ability to transport hemoglobin in the way that they should. It deviates from what the norm should be. And these are pretty easily, when you take biology classes, that you learn to start looking at a microscope and looking at not just what type of cell it is, but the shape of the cell. Learn something about the health of whatever that tissue or that particular cell is. Today, this is done by a machine that takes a cell, it runs it through a high-speed device, and a laser shines a light on it. It knows a predicted volume and shape for a cell, and it does a calculation, and that's part of a standard readout when you go to the doctor and get something like a test called a Chem 20. So it measures what is your hemoglobin level, what is the shape of your red blood cells. That's a common thing that they measure for. So when you take and change the pressure of the solutions due to electrolytes surrounding the cells, it causes the fluid to go in and out of the cells, causing the cells to shrivel. If it's in a hyperosmotic solution, and the opposite is true, and a hypo, it causes the cells to swell as the net flow of water in the cells goes in. Okay, so that's the content that we have. We've got about 25 minutes left or so, so we're going to spend that working a portion of the end of the chapter problems. We're not going to make it through them all, I can tell you that, so we'll spend part of tomorrow doing some of those end of chapter problems. We'll just get where we can get. Okay, so I want to go through and think about that. I got to start the video over again. Start it and stop it. Okay, so it's going to be the